This is a visit teletraining on IFR probability fields. The subject matter experts for these fields are Mike Pavlonis from Noah Nesdis and Corey Calvert from the UW-Madison CIMSS. I'm Scott Lindstrom from CIMSS. These fields use GOES-R satellite information. The two GOES-R series satellites that are in orbit now are GOES-R, which is GOES-16 or GOES-East, that was launched in November 2016, and GOES-S, which is GOES-17 and GOES-West, which was launched in 2018. The channels for both GOES-16 and 17 are listed here. They both have similar resolutions. They have a 5-minute refresh over CONUS. GOES-17 has data quality issues at certain times of the year that are related to a malfunctioning loop heat pipe, which is a cooling mechanism within the satellite. IFR probability detects fog and low stratus. There is no widely accepted definition for what fog and low stratus mean. So the GOES-R definition is based off aviation flight rules. We're looking at IFR probability in this training. Probability of MVFR is greater than probability of IFR, which is greater than probability of low IFR. There are many potential uses for this product. Some are shown here. As a forecaster, you can probably think of more. Traditional fog and low stratus detection products do have limitations. Let me talk about a couple of those. This is an example showing GOES-13 data. I want to call your attention to the enhancement over Pittsburgh and over Corpus Christi. They look very similar. Is this fog and low stratus or elevated stratus? The satellite is seeing the cloud top. It gives you limited information about what's going on at the cloud base. The top of a stratus deck and the top of a fog deck are going to look very similar to a satellite. We will look at the soundings for Corpus Christi and for Pittsburgh. The Corpus Christi sounding is consistent with low clouds and fog near the surface, so it's saturated at the surface and there's a nice inversion. The Pittsburgh sounding has elevated stratus. Mid-level stratus is not going to affect transportation. Low-level stratus will. The traditional brightness temperature difference product will also fail in regions where high clouds or multiple cloud layers block the view of the low clouds. The brightness temperature difference works because clouds made up of water droplets do not emit 3.9 micrometer energy as a blackbody does. Those same water droplets, however, do emit long-wave radiation at 10.3 or 10.7 micrometers as a blackbody. The computation of the brightness temperature, which is used in the brightness temperature difference field, does assume a blackbody emission. Because the emission at 3.9 micrometers is not blackbody, that temperature is going to be cooler than the temperature inferred at 10.3 or 10.7 micrometers. So regions where you have stratus clouds, that is clouds made up of water droplets, at nighttime will show a difference because the shortwave infrared brightness temperature is cooler than the long-wave infrared brightness temperature. You don't have that same kind of brightness temperature difference relationship where you have high clouds or mid-level clouds. IFR probability products shown here was developed to improve on traditional fog and low stratus products. This is the same time as shown earlier, and you'll notice what it has done. It gives information where multiple clouds exist, over North Dakota, for example. It screens out region with elevated stratus, over Pittsburgh. It has a strong signal over Corpus Christi, where IFR conditions do exist. How are these products computed? IFR probability fuses together satellite data. It also uses low-level relative humidity profiles from the rapid refresh. IFR probability is going to be high if you have a stratiform cloud, that is a cloud made up of water droplets, and at the same time you have a region where the model is saying you have low-level saturation, that is saturation within the lowest 1,000 feet. This slide enumerates which of the GOES-R series bands are actually being used. How do you want to interpret IFR probabilities? That's shown in this next series of slides. IFR probabilities greater than 75% mean it's highly likely that fog in low stratus is present. Both the satellite and the model are strongly indicating IFR conditions. So the satellite is saying yes, there's stratiform clouds there, and the model is saying yes, there's saturation. If you have IFR probabilities between 45 and 75%, there's a good chance that fog and low stratus are present. I want to draw your attention to the region over Kansas, this butterscotch-colored region. You'll notice it has a fairly uniform color. That's different from the more pixelated region over western Kansas. The two regions, north central Kansas and western Kansas, show you the effect of high clouds over a fog bank. In the region over western Kansas, where it's red and very pixelated, both the satellite and the model are suggesting that IFR conditions are there. Over north central Kansas, high clouds are preventing the satellite from detecting low clouds, so only the model is telling you whether or not IFR conditions occur. That's why you have that fairly flat field. The model varies much more slowly in the horizontal than the satellite does. If you have IFR probabilities between 20 and 45%, neither the satellite nor the model are strongly indicating that IFR conditions are there. One is moderate and one is weak. This kind of probability typically occurs as fog is developing or as fog is dissipating. If you have IFR probabilities less than 20%, the satellite is probably not detecting clouds, and the model is not detecting saturation, so weak indicators from both of them that IFR conditions might be occurring. There is also a cloud thickness product. The cloud thicknesses are calculated empirically. The emissivity at 3.9 micrometers is compared to a lookup table. The lookup table contains values of 3.9 micrometer emissivity and SODAR observations of cloud depth that were created using observations off the west coast of the United States. As the sun rises and sets, the reflected component of the 3.9 micrometer solar signal changes very quickly. GOES-R cloud thickness is not computed for times around sunrise and sunset. If you take the observation of GOES-R cloud thickness just before sunrise, the last one that's there, you can use that to help predict when radiation fog will dissipate. This computation is valid only for radiation fog. I'll show you an example of that in a bit. IFR probability products have a better statistical relationship to IFR conditions than does the traditional brightness temperature difference product. And I've given you two reasons why you know this has to be true. One, IFR probability products screen out regions of mid-level stratus. So the brightness temperature difference product there will be telling you that fog is present, but IFR probability is telling you no, it's mid-level stratus. You can also have regions where there are cirrus clouds, so the satellite cannot see the low clouds, but IFR probability products will be using the model data there and the low-level saturation in the model to suggest that IFR conditions are present. IFR probability has superior statistics to the brightness temperature difference in identifying regions of IFR conditions. There are a couple of known issues. There are boundaries in the IFR probability products where different models are used for the low-level saturation. If you are making forecasts over CONUS or over Alaska, this won't be an issue. If you're doing forecasting over the high seas, you might see a seam where the CONUS grid or the Alaska grid borders the regional grid that is used, or where the regional grid borders the GFS. There's also a day-night discontinuity. A couple of things to note here. This is GOES-13 imagery, but you see the same kind of thing with GOES-R. When day turns to night and when night turns to day, note that GOES-R cloud thickness is not being computed for about 90 minutes around the terminator. You'll also see changes in IFR probability values as day goes to night and as night goes to day. IFR probability values are generally a little bit higher in daytime because the algorithm is more confident that a cloud is actually present. This is because the visible data can be used during the daytime as a cloud mask. So if you're more confident that a cloud is present, you're more confident that IFR conditions are occurring. I'm going to show you 5 different cases using GOES-R. Here's a question for you. Based on this night fog image, is there fog in central Illinois? The region I just circled. Do you think there are obstructions to visibility at the surface and low ceilings there? Maybe you're used to looking at the night microphysics RGB to determine whether there's fog. Same question, is there fog in central Illinois? Here are the 10Z observations to go with the satellite image. There are no IFR conditions there. This is a mid-level stratus deck. If you look at the sounding in Lincoln is here, you'll notice there is mid-level stratus indicated in that 12Z sounding. What does IFR probability look like at this time? IFR probability values are fairly low. The rapid refresh model here did not show any low-level saturation. IFR probabilities therefore were diminished in regions where we had the stratus deck. Up over north central Indiana, notice that you do have low-level saturation in the lee of Lake Michigan around South Bend, and IFR probabilities are fairly high there. Here's another example. This one's over the northeast during the daytime. Where are the IFR conditions during this frontal passage? I have the observations on top of this so you can see where they are. It's hard to see a coherent image right away, however. But if you look at the IFR probability fields, you see a region of higher IFR conditions that stretches from northeastern Pennsylvania through Vermont and northeastward into Maine. One thing that you might be able to do in AWIPS is to use the visibility to show the IFR probability underneath the visible imagery, so you get a better feel in one image where you might have IFR conditions. IFR probability considers RAP saturation in the lowest 1,000 feet above the ground. There is knowledge of topography in the field. So here we're looking at a case over Idaho. Look at the visible image shown here. We do have ceilings and visibilities plotted. Can you tell immediately where the IFR conditions are likely happening? Here's the day fog product, 3.9 minus 10.3. I'll just toggle between the visible and the day fog. You know where the higher topography is. Does that match up where the higher IFR probabilities are? And the answer is yes. So if we toggle between this field and the high-res topo field, you see exactly where the IFR probabilities are highest, and they're in the region where the highest topography is. You see this a lot around the Central Valley of California as well. So we're on the west coast of the United States, strong northwesterly flow underneath a cirrus shield. Where are the lowest visibilities in this field? It's difficult to tell from the satellite alone, because of course the satellite can't see the low clouds, it's only seeing the cirrus deck. But if you look at the IFR probability for this time, you see a field of high IFR probability confined to the coastal region of Washington and Oregon, and also to regions over northern Idaho. Note how the IFR probability field out over the Pacific Ocean is fairly uniform. This has all the hallmarks of an IFR probability field that is determined mostly by model data. You do see some pixelated regions out over the ocean. This is where there are holes in the high clouds and the satellite is able to view down to the low clouds near the surface. If IFR probability fields can access both the satellite data and the model data, you get a higher IFR probability. If IFR probability can only use the model data, the actual magnitude of the IFR probability will be a little bit smaller. Here's an example over Texas. There are high clouds that are blocking the satellite view of the low clouds. So you can definitely see the night fog brightness temperature difference. So there is stratus in here and there is fog, and there are also cirrus clouds. It's difficult to see at a glance where the IFR conditions are occurring. You can kind of infer that because I've put the observations on here, but if you didn't have the observations, it would be a hopeless task to use the satellite data alone to say, oh, that's where the IFR conditions are. Here's the nighttime microphysics RGB that can also be used to identify stratus clouds. But that's not telling you where the clouds are sitting on the ground, that is where there is fog and IFR conditions. IFR probability fields better inform you where the lowest ceilings and reduced visibilities are because it's combining the satellite data with low-level saturation from the rapid refresh. Toggling between the two of these helps you understand how the mid-level stratus is screened out and where the region underneath the cirrus deck is filled in. If you're using this product and have to choose between GOES-16 and 17, keep in mind that there's parallax with it. Even though these are low clouds, if you are some distance away from the satellite, there's going to be a parallax shift. Here we have the GOES-16 IFR probability over the Bay Area, and you'll note it has the low clouds over the peninsula, over San Francisco. If we look at the GOES-17, the low clouds are out over the ocean, which may be a better solution. So let me just toggle between the two of those. The pixel size with GOES-17 on the west coast is smaller than the pixel size with GOES-16. Same thing is happening up in the Pacific Northwest. Here's the GOES-16 IFR probability and the GOES-17 IFR probability. There's a parallax shift between the two, and the pixel sizes are a little bit different. River valleys are probably not resolved by the rapid refresh. So these narrow river valleys in northwestern Pennsylvania, the rapid refresh likely isn't giving you much of a signal there. At the same time, up over the western tier of New York, you have a region where the satellite signal is probably weak. The model is indicating that relative humidity has increased in the lowest 1,000 feet. This might be a timing issue in the model of fog development. Farther to the west, over northwest Pennsylvania, you likely have both satellite and model indicating the presence of IFR conditions. You can use the GOES-R cloud thickness product to estimate fog dissipation time, and that's shown in the scatter plot with the best fit line applied to it. Remember, the GOES-R cloud thickness product is not computed for about a 90-minute window on either side of sunrise or sunset. The x-axis is the number of hours after sunrise for the fog to dissipate, and the y-axis is the GOES-R cloud thickness that you observe from this product just before sunrise. A second reminder that this is valid only for a radiation fog. You can use that value to estimate how long it will take the fog to dissipate. Here's an example of that using GOES-13 data. This is an 11Z image in late March, and if we look over southern Georgia just before sunrise, the GOES-R cloud thickness there was about 1,000 feet. If you look on the scatter plot, 1,000 feet correlates pretty well with a dissipation time of about 3 or 4 hours. So about 3 or 4 hours after 11Z is when you should expect this fog bank to have dissipated. 12:45, there is no GOES-R cloud thickness product. We're still in the window around sunrise when it is not computed. You still have IFR probability, and the visible image is also showing fog in the region. At 13:45, there is a GOES-R cloud thickness product being created again. The fog bank has not burned off yet. At 14:15, it's almost gone, and at 14:45, it has gone. Use this product from one day to the next to help you estimate when fog is going to burn off. Adjust your estimates based on your local knowledge and how these values have operated within the near past. One of the things the GOES-R probability brings to the table is much better temporal resolution. You can use this product to estimate when IFR conditions might be overspreading a region, in this case, Tampa Bay. You'll also notice in this animation how at the top of the hour, the IFR probability fields change a little bit. There's a pulsing there. Every hour, new rapid refresh model information is incorporated into the IFR probability fields. You can expect a change every hour. Usually, this is just a small change. This next example compares IFR probability with the night fog brightness temperature difference and the nighttime microphysics RGB. This was a case where there were dense fog advisories over much of the Deep South. High IFR probability covers most of the southeast part of the United States. It overlaps pretty nicely with the dense fog advisories. Let me just toggle between the IFR probability field and the night fog brightness temperature difference. There are regions in Alabama where we have high clouds that are masking the low clouds underneath. There are regions over Tennessee where we obviously have stratus clouds, but not IFR conditions, so that mid-level stratus is being screened out by the IFR probability. If we now toggle between the night fog brightness temperature difference and the nighttime microphysics RGB, one of the things that I found interesting in this particular example was the coastal fog along South Carolina shows up fairly nicely in the IFR probability field, but not in the night fog brightness temperature difference or in the nighttime microphysics RGB. There are many different products you can use to identify fog. Make sure you understand the strengths and weaknesses of the ones you are using. IFR probability fields are more skillful than a simple brightness temperature difference product, the night fog brightness temperature difference, or the nighttime macrophysics that uses as an input the night fog brightness temperature difference in identifying regions of IFR conditions. The reason for that increase in skill is because IFR probability screens out regions of mid-level stratus, and it adds regions underneath cirrus clouds where satellite-only detection cannot view the fog. The satellite only sees the cirrus in that case. There are additional products, information, and training materials at these websites. In particular, there is a fog blog where you can see individual cases that are categorized geographically. You can go to this website and choose the appropriate category. If you have comments or questions, Mike Pavlonis is the subject matter expert on this product, and Corey Calvert can also answer questions, or you can send them to me, Scott Lindstrom. That's the end of this training. Thank you for listening.